Welcome back, everybody, and welcome to the last lecture of this semester. And I think this place is a little bit better than the one we had up in the reading room. And probably next year we will try to find a slightly different solution. But anyway, today the idea is to wrap up about gradient methods or gradient boosting. And as you will see, these methods, gradient boosting, they are kind of lookalikes of gradient descent, which you've seen before. And the basic idea behind these methods is to use what we call a weak learner, and use this weak learner through iterations to improve the quality of the model. And you can do that in different ways. One of these was the one which we introduced last week, which is called ADA boost, or adaptive boosting, where you simply adapt by every iteration a better and better approximation to the data you are looking at. And this ADA boost, what we did last week was to look at that for a regression case. And then we started to look at what is normally called ADA boost. And that is the algorithm for classification. And the basic emphasis of this type of boosting methods is you putting emphasis on the wrongly classified results. So in every iteration, you put more and more emphasis on those results which were wrongly classified. So I'm going to go through the mathematics of that. And after we're done with that, we are going to look at gradient boosting, which is one of the more popular methods for classification in particular, but it has also been used for regression type of problems. And then we are going to have a kind of summary and look at what we've done through the semester and point to other courses for those of you who would like to continue with machine learning, because there's a good selection at university here with more advanced topics. So there's a series of videos here which you can look at if you want to about these methods. The last lab session, and you should find the exercises in the normal place. I've also put the announcement on Canvas. The last exercise is actually just a course review, or you giving us a feedback. Things which have been working well and things you have a suggestion for improvements, etc., etc. And that is the last of the 10 exercises. And again, like all the other exercises, it counts 1 point. So that means that if you have an average score of, let's say, 82 on the 3 projects, and you've done all the 10 weekly exercises, you get 92, which is an A. Okay, so we would obviously love if you give us some feedback, and please be both critical, and if things are working well, we will also like to hear about that. But anything which can improve the course is obviously very, very welcome. Okay, so just a quick reminder from last week. One of the very popular methods is the one which is called the random forest. So all these methods are ensembles of trees. In a way, we can just call them forests or woods, if you prefer that word. And the random forest is actually a very simple algorithm. It starts with a decision tree, but then you decide how many trees you want to make. And in order to avoid that a dominant feature is the one which creates all the trees, so the root node would be given by the dominant feature, then you select randomly the features which you have at hand. So if you go back to this cancer data, if you had 30 features, you would select randomly, let's say, only 10 of them. So a kind of rule of thumb which is being used is that you take the square root of the number of features. So in this case, you would take the square root of 30, and you select only some 5, 6 features randomly. And then you find the dominant feature, which you would use to define the root node. And then you keep going like that till the final depth of the tree. So the tree is typically defined by the depth. That means typically how many internal nodes you want to have, which when you look at this Gini algorithm, it means that you have a binary split, yes, no, true, false. And then you decide how many times you want to do this true, false game. And the depth of the tree is defined by that. Then you can also define another parameter, which is called the number of leaves. And the number of leaves are typically, if you're doing a regression type of problem, how many data points you want to have in a specific region. So when you do a regression type of problem, the result is the average value of all the data points in a small region, which you have narrowed down by making this tree. So the way you do it, as we discussed some 2 weeks ago, is actually pretty simple, the way you split the tree. And when you have an algorithm for the tree, you can then decide whether you want to do bagging, which is actually you constructing trees by bootstrap, by resampling your data set, and then simply constructing a new tree every time. And then you can decide about the depth of the tree. The problem there is that the trees are all lookalikes, and you can have strong correlations between each tree. And that can lead to a higher variance. Then we have the random forest method, which is a very, very popular method. And it's also extremely simple to use. Either you write your own code, or you use scikit-learn, which has for the classification, it's called a decision tree classifier. This is for the tree itself. And in this set of data, we are using the cancer data, which you had in project number 2. We are comparing with logistic regression. We do a plain decision tree, which is now given a free number of internal branches. So that means that we don't put a limit to it. And then we have the random forest, which you would simply call by random forest classifier. And in this case here, we're just making 500 trees. So this is the number of trees we are setting up. And here we use the entropy as a criterion to split the nodes in true, false. So these are just ways of doing that. And we saw that last time that the random forest gives normally a pretty good classification of the data. And in this specific case, you could see that we had a 97% here, and we had a very small error on the false positive and also on the false negative. So which is this method is actually doing pretty well. Now we are going to see that when we move to gradient boosting methods, we're actually going to get much better results. We will get a classification error, which is 0, basically. So these gradient boosting methods combined with a library, which is called XGB, where we mentioned last week, this stands for extreme gradient boosting. This is actually just a gradient boosting method being implemented in a very efficient way. And this library is a kind of standard library which everybody's using in classification type of problems. But for those of you doing this in project number 3, a random forest is a typical method which you would be using for a classification or regression type of problem. Any questions so far? Okay, so and here you have the classical ways of presenting the data. As I said some time ago, I normally like the confusion matrix, but people would also present the ROC curves or the cumulative gain, where you actually plot the ratio between the positive false towards the positive. No, I always have to look it up. I don't remember now. Sorry. I always have to look up what these what stands on the x-axis and the y-axis here. To me, the confusion matrix is pretty intuitive. Now, you can compare that with bagging. You can do bagging in many, many different ways. In scikit-learn, you have both the random tree classifier, but you can also do the bagging classifier, which you have here. So and there you just take a set of decision trees and I make 500 trees. And in that case as well, the prediction is actually pretty good. Now, this was a short repetition of things we did last week. And what we also did last week was to look at boosting. And in boosting, what we actually do is to gradually build up a final function where M now would stand for the number of trees we are going to make. Alternatively, it could simply be the number of iterations we make with a given function. And the example which you had here in the lectures from last week, we simply took a plain regression case. And the whole idea then is actually to establish a measure of the quality of this model, f of n. And you would simply then compute at every step, you will simply optimize the cost function, which you have here. And with that optimization, you would then find the optimal values, which we have used to parameterize this function, where we have a function b, which is a base function. We have a parameter beta and a parameter gamma. We take the derivatives with respect to these parameters every step. We find them, and then we keep iterating like this, where this b could be a decision tree, or as we showed in the exercise or in the examples last week, we let this b just be a polynomial of first order. So that's a very, very simple regression type of model. So what you would do in every step is to calculate the derivative with respect to these parameters. And then you find the optimal ones, and then you simply make a fit. And in that fit, you find the new function, f of m. And you would typically start with just you could even start with 0. So in every iteration here, when you calculate these derivatives, in this particular case, it's a very simple function, then you need to evaluate these derivatives numerically with the gradient descent. So gradient descent comes in everywhere. You can't escape it. And when you've done that, you have found the parameters beta and gamma in that specific iteration. You solve the equations, which is a set of nonlinear equations here, and then you find the new value f1, and then you simply keep updating this again and again, till then you have a final function, which you are satisfied with. So for the regression case, what is pretty common to do then is either to use a function like the one I showed you, or to take a decision tree. And then you would normally make it shallow in the sense that you want to have a tree which is easy to train. So in every such iteration, you don't want to have too complicated objects which you're optimizing. And this first order polynomial is a simple case which you even have analytical expressions for the optimal parameters. Okay, so what I want to do now is to move over to the classification problem, which we started to look at last time. So I'm going to bring back the standard ingredients of a famous algorithm, which was introduced around 2000, which is called ADA-boost, adaptive boosting. And this is a method which puts the emphasis on the wrongly classified elements. So in every iteration, you put emphasis on those, and hopefully that is a way to speed up the iterative process. So let's remind ourselves about ADA-boost. And when we've done that, we are going to move into gradient boosting. And gradient boosting is going to be slightly different in the sense that we are going to let the function we approximate to be given by the gradient of a cost function. And that way we are going to introduce, again, gradient descent with its standard parameter, the learning rate. And that leads to the famous gradient boosting method. So many of these methods in philosophy are actually pretty simple and straightforward. And you will see also from some of the programming examples in the lecture notes that they are pretty straightforward to program. So if you want to write your own program, this is something you could have done easily as a part of one of the projects. But now for the final project, we normally recommend to use the libraries like you see in scikit-learn or extreme gradient boosting. Okay, so let's switch back to the whiteboard and look at ADA-boost. So in ADA-boost, adaptive boosting, ADA-boost. This is the way you will encounter it in basically all textbooks is as a classification problem. So what we have then is a set of data D, where we now have the classical X and the output Y, X1, Y1, etc., all the way up to X of n minus 1 or Y of n minus 1. Now, you can tailor this to multi-class problems, But in our case, the y of i's take values like -1 and +1. So this is a typical true-false case. You can always change 0, 1 to -1 and 1. And you will see quickly why it's more convenient to have it as -1 and +1. Then we are going to define a set of weak classifiers. And this set of weak classifiers are classifiers which we are simply going to label as a B1, a B2, up to a B of M. That's the final classifier. So each one of these classifiers is something you can think of as a tree. So that means that we are going to make M, uppercase letter M, trees. So these classifiers, these weak classifiers, they're also going to be functions. So this is actually, this y of I is actually a function of x of I. And now we are going to make such a function bj, which will be an input of x of I. That is also going to take values either -1 and 1. So this is what we want it to have. And we are going to build gradually these functions so that the final function which we want to have, so this is the one we are going to train after a given number of iterations. We have suppose we have done m-1 iterations, then this is going to be given by some parameter alpha1 times b1 of x of I plus, and this goes all the way up to alpha m-1 of b of m-1 of x of I. And then we continue like this till we have reached the final value m. And when we have reached that one, we have produced actually m such weak classifiers, which you can think of each of them as one tree. Or, if you prefer, some other simple type of function. So the question now is, how do we find these parameters? So the function which is done or is used in this ADA boost, the way to find the parameters is to define a function, the error function, which is now our cost function. So which is now given by a sum over all the data sets which we have. And then we multiply the exponential with minus y of I times this function c mx of I. And then we just recall that this y of I is either -1 and 1. And this function, if we have the c m of I, this function is also either -1 and +1. So we do actually train a tree every case, and that returns either -1 or +1. It can be correct or it can be wrong. And now you will see why this method, so this is another way of actually setting up the cost function. There is nothing which hinders you using the cross entropy or other types of functions. And you will see in the literature that people have tried many different types of functions. But the original formulation of ADA boost was given in terms of this specific function here. So this is our loss function, which we want, or cost function, which we want to optimize as a function of these specific functions B, which then lead to the function C here. So in our case, what we have is that if we then look at the product of y of I times cm of x of I, that is equal to 1 if correct prediction, if predicted correctly, and we have y of I of c mx of I is equal to -1 if a wrong prediction. So this is pretty straightforward to see, because if you are you have to predict +1, and you predict that correctly, you have +1 times +1. So then you get +1, obviously. If you predict wrongly, and you should predict +1 and you predict -1, you get a minus. And that means that if you look at this exponential, what happens then in the exponential here is that the correctly predicted get e to the -1, the wrongly predicted get e to the +1. So that means that the wrongly predicted values have a higher emphasis. Okay, so let's just continue and see how we can rewrite this. So we are going to do a slight rewrite now because we know that this function Cm of x of I is actually given by the previous value of x of I plus this alpha of m times b of m of x of I. So b of m is our weak classifier, which we now want to use to predict either -1 or +1. And this alpha becomes just a parameter, which we are going to tune in the calculations here. So the question is now, how do we find this alpha? The trick now is simply to rewrite this error. So we rewrite it in terms of this new function. So we have an n minus 1, and then we have the previous value, e to the minus y of I. So we have a Cm of x of I. And this is multiplied with e to the minus y of I of alpha m times b of m of x of I, like this. Now we are going to define a weight here, a wi equals 0. This is the first iteration, which is equal to 1. Actually, these weights are given by the sum of the data of 1 divided by n. But now we just put the initial weight to 1, and then we define a new parameter, which follows after the number of iterations. So we define this one as e to the minus y of I times Cm minus 1 of x of I. So what does that mean? Now, this value here, this should be minus here. There should be a -1. Let me just correct it. I forgot the -1 here of x of I. So this is something which we have defined from the previous iteration. So this is known to us. So that means that we can actually leave that in terms of just this constant, which you see here. So this is a known quantity. We determined that in the previous iteration. So we can now rewrite this error in terms of that constant. So we define it like this, I equals 0 to n minus 1. And then we have this variable wi of m. And then this is multiplied with the unknown parameter alpha m. And then we have this function b of m, which is just a weak classifier, which we have defined. And that could be a shallow tree. So we are going to split this new term into those points which are correctly classified and those which are wrongly classified. So if we now look at the correctly classified, so if we now move on a little bit, so a correct classification, and we are training the function b, and we are going to leave out this alpha because we're going to find a recipe to calculate this alpha. So what we have is a value of y of I times this b of m, this unknown function, or the function is known, but we need to train it. This is +1 if it's correct, because if you have +1, which you won't predict, and you predict +1, then you get +1. And then if correct, so if correct classification. So remember now that this b of m, this is now your simple decision tree or your weak classifier. And that is now trained on your data. And every time you train it, it gives either -1 or +1. And then we know that this y of I times this b of m of x of I is equal -1 if it's wrong. And we are going to use this to define the parameter alpha. So that means that what I can do then is the following. I can rewrite this error in terms of a term which I have y of I is equal to bm of x of I. So these are the correctly classified ones, multiplied with the previous value of e to the minus alpha m, which is the unknown parameter, plus a y of I not equal to bm of x of I. So I'm looping over all the wrongly classified. And this is simply given by wi of m. And now I'm simply getting, when I'm doing the wrongly classified ones, I obviously have a minus one. So this becomes equal to alpha of m here. Then I can manipulate this function here. And what we are going to get then is a final equation for these unknown parameters alpha. So we can rewrite this function in terms of the following. I can now simply sum over all the correctly classified ones plus the wrongly classified ones. So just run over all the data. And now I'm simply setting wi of m of e minus alpha m plus, and then I'm simply summing I equals 0 to n minus 1. And then I have my wi of m. And this is the case when y is different from bm of x of I. And then I have e of alpha m minus e of minus alpha m here. So this is just a plain rewrite where I simply manipulate the equation. And the only part which depends on b of m is actually the last term. So this term which you see here depends now on this function b of m. Now the first term is just a free sum here, but I need to find an expression for this alpha m here. So we need to minimize the error by optimizing this alpha of m. So the way we are going to proceed now is simply to calculate the derivative of this d epsilon r, the error, with respect to this parameter alpha m here. And if I do that, this is simply minus, and then I have the case here with y of I equal to bm of x of I, and then I have this wi of m of e to the minus alpha m, and then I have my plus, and then I have the sum over y of I different from b of m of x of I, and this is given by wi of m, and then I have e to the alpha of m, and we want this to be 0. Now we can manipulate this equation here, and what we will find then when we manipulate the equation, so I just give you the final answer here, we can then find that this alpha of m is now defined as 1/2 of log, and then I have a sum over the correctly classified of b of m, and this contains wi of m here, divided is actually not so difficult because it's just you reordering these equations. So you can define then what is called the weighted error. So this is pretty common then. Define weighted error. And I'm going to call this for an epsilon of m. So this is simply now given by the wrongly classified y of I, different from b of m, of wi iteration n, and divided by the total number of n over all the data of wi of m. And then if I do that, I can just rewrite that function for alpha of m in terms of 1/2, and then I have the log, and then I simply have 1 minus this epsilon m divided by epsilon m. So this was the ADA boost algorithm. So that means that for every value of m, we compute this weak classifier, and that gives us either plus minus 1. And when we have that, we collect then simply the sum over all the values which have been correctly classified, those which are wrongly classified, and that defines simply this function. And with that, we have a recipe for this alpha of m. So to implement this one means that we would start with a guess for this function b c of m, as we called it. And that could be even set to 0, which is often the case. And then in the next iteration, we call our weak classifier. We then find out which one are correctly classified and wrongly classified. When we have that, we can then set up this function alpha of m. And with alpha of m, we can then go back. So if we go back then, with alpha of m, we can then finally simply set up the function here. So this should be a plus here. We can then simply set up the previous value, which we had, plus alpha of m times the new b of m. And b of m is nothing but the same function which are calling all the time. Some people change it by making the tree deeper and deeper. This is a possibility. But in general, this b of m is a weak classifier which you have chosen. So then you keep calling it. You update this parameter as alpha of m, which puts emphasis on the wrongly classified results. And then you keep going till the final tree, which is your final value of m, which you would then define here. So you would actually perform this up to m times. And this m times represents then the number of trees which you have. This is the AdaBoost algorithm. And this has also been extremely successful in classification problems. And it's also, as you will see from the programs which we have in the Jupyter notebooks and the lecture notes, it's very easy to program yourself. You simply need, you could actually program it yourself using the decision tree, which comes from scikit-learn. And then simply call that one again and again, and have your own program for the update of the parameters. Now, if you dive into the literature, you will find other ways of actually setting up this cost, because our cost function is now this error, which simply sums over the case of misclassified and correctly classified. But you could actually change that function. And there are many, many different ways of doing that in the literature. But I wanted just to point to you the simplest possible one, and as it was introduced back in 2000, roughly. I think it was a little bit before that. So the algorithm for AdaBoost is actually pretty simple. So let's just set it up here. In order to finalize. So you would clearly need to define your data set, define the data set D, x0, y0, x1, y1, etc., up to the final data. You need to initialize the weights. And it's pretty common to actually set the weights equal to 1 divided by the number of data points. So we just put it to 1 in the beginning, but it's pretty common now to just define it like this. So you would have a 0, and this goes all the way up to all the possible weights which we can have. And it's pretty common to put them equal to 1 divided by the number of data points. Then we need to define the error function, or the function we want to optimize. Function to optimize. And in the original version of AdaBoost, that function was given by this error, which we called e to the minus y of c of m, where we now are summing over all the data points which we have here. I, and we have an I here, and this depends on x of I. And then with a weak learner, we need to define that. So we define a weak learner. which we just call a B of M of X of I. And that, as I said, can be a decision tree, and that returns values for this specific classification problem equal to -1 and +1. And then we would now simply start by producing a given number of trees. So we would then start, when we have done that, we would have 4i, or m actually, the number of trees which we have up to n. Then we have the weak learner we are going to optimize. So we define, calculate the error as defined in the equations previously. We calculate this error, then we compute this alpha of n, which is equal to 1/2 of the logarithm of 1 minus this error which we defined, epsilon of m. Then the next step is actually to update this Cm of x, which is equal to Cm minus 1, the previous value, plus this alpha of m multiplied with b of m, which is a function of x here. Then we update the weights. Update, let me correct that one. So what we would have then is just to update wi of m plus 1 is equal to wi of the previous value multiplied with e of minus y of I times alpha m times b of m, and then I need the parenthesis x of I here. Now, we also need, when we have updated these weights, it's common to normalize them. So they are typically normalized to 1 in order to avoid that these weights blow up. So after we have found them, we take and normalize them, and then we keep going till we reach the final value of n. And that is the end of the classification problem. So the next step here would be to update. So we would then have for I inside this loop, from 0, 1 up to n minus 1 here, then we would normalize the weights. This wi of m plus 1, so we would simply then sum over all the data points which we have, and then simply normalize these weights of m plus 1, and we require that they normalize to 1. So we end this loop, and then we have the final end loop over m. Over n. And what we have then is our final function c of m of x, which is the one we will use to make predictions. So it's actually pretty straightforward. And so if you have a decision tree, or if you use any other classification method, you could, a weak one, which is fast to update, because you see, you're calling this many, many times. And that means that you want something which is quick to call. Okay? So if you like this, we are going to make a small change, and that change is called gradient boosting, which is actually a method which brings back gradient descent. So in a certain sense, we are closing the loop here because the gradient descent methods have been pervading everything we've done, but now we are going to use them to update a function. So the basic philosophy is the same of you having what we call a weak learner, but now we are going to update this one by calculating the gradient of the cost function. And then we're going to multiply this one with a learning rate in order to eventually avoid that this gradient blows up or that it just vanishes. So let's look at the basic philosophy of gradient boosting. Unless you have any questions, does it sound pretty straightforward? I think you could all, with some slight rethinking, that you could easily implement these methods, especially if you could just use a decision tree from scikit-learn. and then simply plug that in and call that again and again. And the only thing you need to do is actually to count the number of wrongly classified and correctly classified, and then calculate this quantity, and then you calculate this one, and then you simply update the functions. Okay, so let's look at the famous method, which is winning so many competitions. This is also something which I hope you're not intimidated, but it's actually a method which is also not that difficult to implement yourself. And the basic philosophy of the method is now to start again with this kind of weak learner, which we want to approximate. So we are going to have a function f again. So this is my attempt at the letter f. I hope you can excuse me. So I have some letters which, since I was a small kid, I was never able to write properly. And I don't know, I can't explain it to you. I had F and R and S. So I had the teachers in elementary school, and I'm that old that the teacher would beat us if we didn't write correctly. I guess you guys have not experienced that. So I had F, S, and R. And this has, it still stays with me. Okay, guys. So we would then have a new set of functions. So we would have this as a function of these different values of x, n up to -1. And we are going to make a model again, where this m stands actually for the number of trees which we're going to construct. So we would have a sum from m equals 0 up to this n. And then we are going to try to find a way to optimize and find these functions. And these f's are, again, some kind of weak learners. It can be a function for the regression case or for a classification problem. We are going to define a function which is now a function of this f. And this is now given by the sum over all the individual losses, as we call them. So an L of y of I. So this is a data point. And then we have this function x of I, which is our prediction. And we are going to find the optimal f by simply optimizing this function, which is the cost function, as a function of these f as parameters, and the cost function c of f. Now, one of the ways by which we can now do this is actually by looking at the standard gradient descent. So when we now look at these functions, what we could do now, so one way to find these f of m's, and these f of m's are going to be given by the previous value minus, and now we are going to put in a parameter, which is a scalar. This is a rho. So this is a scalar parameter. And then there's going to be a function g of m of x here. And this is just the gradient of this function n. So that means that this g of m, so we are going to have a g of m of x of I, is simply going to be given by the gradient of this function of y of I, and then we have the fm minus 1 of x of I. So we calculated at the previous value, and we write it like df of x of I. And this is evaluated at, so let me just bring this in here. So this f of x of I is given by the previous value which we had. So we have an expression for the gradient. It means that we calculate this gradient with the previous function value we found. And then we take and optimize the function C in order to find this parameter rho of m. So the next step is then to define this step length or learning rate, as we've called it. Rho of m, this is actually what we have called the learning rate. And then we will simply define that one by finding the optimal one, which is now the minimum. We take the argument of the minimum as a function of rho of the function C of f. So this is not exactly gradient boosting. This is just a kind of steepest descent method, which is less used in this gradient boosting machinery, but you could actually set it up like this. Now, what we are going to do after the break is actually set up the more used algorithm for the gradient boosting. But you see the basic philosophy here. We take a cost function like this function L or loss function. We calculate the gradient of it, and then we are updating the function with the gradient times a small step. So you could think of that as a sequential way of just getting a better and better approximation to the function. So this is the basic philosophy, but after the break, we are going to set up the standard way by which a gradient boosting is implemented. And it is implemented by actually looking at the difference between the points you want to reproduce and the prediction you make. So you're optimizing the residual. That means the wrong or the error you have for every iteration. And that's the one you're optimizing. So you're going to calculate the gradient with respect to the error you're making. And that is a much more efficient way of doing it and leads to the popular gradient boosting algorithms, which are widely used and are, again, actually pretty simple to implement. And you will see that from the final algorithm. So we will use some roughly 20 minutes of the next lecture to actually give the algorithm, which is pretty straightforward. And then after that, we are going to do a summary of what we've gone through during the semester. Any questions to gradient boosting and adaptive boosting and so on? I love these methods. They're in a way intuitive, and they're also easy to implement. I hope you believe me when I say it's easy to implement. Always be skeptical when somebody says something is easy to implement. Okay, let's take a small break then, eh? So one of the reasons why this approach is less used is that this kind of method actually optimizes f of x at a fixed set of points. However, it can be more difficult to generalize it in order if you want to find a function which represents the best possible approximation to the problem. So the standard gradient boosting is, if we now look at the following example, so let me try to expose the basics of the gradient boosting. So suppose now that we look at a regression type of problem, which I often find a little bit simpler. So we have a function C, which we want to optimize, which is now simply given by a 1 over n, the number of data loop over the data points which we have the y of I, and then we fit a function, f of x of I squared. And we know that if we just go back to what we did previously, this y of I tilde is given by this f of x of I. If we think back to project 1 and regression, so this is just our predicted value. Now, what we could do now, when we do a gradient boosting, is actually at each step, what we do then is the following. So we now define a function f of m plus 1. So this is after a given number of steps. And this could be the number of decision trees which we have created. And we have a function x of I plus an r. So this is now I'm actually using the two letters which I always struggle with, as I mentioned before the break. And this is going to be equal to y of I. And this function r of m of x of I is actually y of I minus fm of x of I. And this is normally what we call the residual, or the error which we made at that specific step. So the gradient boosting aims at fitting this residual so that in each new f of m plus 1, what we are attempting then is to correct the errors in the previous function value. So the gradient boosting, what it attempts at, or aims at fitting or optimizing this error which we do. Rm of x of I to be the residual of this. So the residual is just y of I minus fm of x of I. So that means that if I now look at the function which I picked for regression here, what I would have then is that the dc of df of x of I is then simply equal to minus 2 divided by n. And then what I have then is y of I minus f of x of I. So that means that this is just equal to minus 2 divided by the number of data points multiplied with the residual. And what you see then is that this new f of m of x is simply equal to this f of m minus 1 of x plus this rm of x. And the gradient boosting, in a way, is to, it can be generalized to some kind of gradient descent for plugging in a different loss function and its gradient. So what we are setting up then is essentially the following recipe. So we have an f of m of x, which is equal to an f of m minus 1 of x, plus the function which we are optimizing. And this gives us, what we have here is simply in the optimization is the gradient of the loss function. So we are simply optimizing this function here, n minus 1, and then we have this L of y of I, and then we have an f of m minus 1 of x of I, plus this rm of x of I. And this is a function which we are optimizing. Now, this is normally changed a little bit. So what is normally done is to add an additional parameter here, which is going to be something you will recognize as the learning rate. And this is done in order to have this equation here to converge better. So what is commonly done then is, in addition to this one, is to actually define a learning rate. So let's now set up the algorithm. So the essential element is actually the one which you see here. And with this one, we can now set up the algorithm for gradient boosting. So let's set up the algorithm for gradient boosting. And now we are not specifying this to a decision tree. So if we specify this to a decision tree, there can be some smaller subtleties which deal with how many points we want to have in a specific region. That means when we come to the final leaf, how many data points we want to have in a final region. So I'm just leaving this out because when it comes to the specific function we want to plug in, then this could be a decision tree, but it could also be, if you're doing a regression problem, it could be a simple function. So the basic elements in this algorithm is obviously the first step, where we initialize a model. So we would then have a function which we would call an f0 of x. And sometimes you could just put that one to 0, or you could simply just take your loss function and take the derivative of that one. So there are many ways to initialize it. You would also, so that would be the first point. You obviously need to set up the data set. You need to define the number of iterations you want to do, this variable m. Then, if we now have done all the initializations, then what we need to do is to have an outer loop for m equal 1 up to this n. So this is going to be, if we're dealing with decision trees, it's going to be the number of trees which we want to compute. And then for every tree here, we need now to compute the difference between the prediction and the output. So the first step here now is to compute these gradients. And you would obviously do that at each level. And you're going to compute that one by simply defining this RIM. And this M now runs over all the data points which we have. So this is 0, 1, 2, up to n minus 1. And this function here is now going to be given as minus, and then we have the derivative of this loss function for this variable x of I. And then we have a y of I calculated at fx of I. And this is always evaluated at the previous value. So this is given by an f of m minus 1 of x of I. And that means that when we have done that, so we have this RIM, the next step here is to fit, if you're dealing with decision trees, fit a decision tree to the residual. Which is this RIM, given points. And you also have to be a little bit careful with the number of leaf nodes which you have. But then for each tree then, or for each, if you're dealing with decision trees, for each leaf node, so this is actually the final part of the tree. Then, because normally it's pretty common to use decision trees with these methods. So then for each of one of these nodes, you would then calculate this gradient. So you would optimize, you would calculate this function gamma of m, and that is given by the argmin, where you have now a optimization with respect to this parameter gamma. And the function which we are going to look at is something which I will put on the next page. So let me put that one up. So I'm going to sum over all the points which are present in a specific leaf node. So we will have a variable j. So m is the specific iteration we are looking at. And this j is the specific leaf node which we're looking at, if this is a decision tree. If we're just dealing with a standard function, like a regression type of function, like a polynomial, then this is a little bit simpler, because then we would not need to classify these leaf nodes. And this is going to be given by a function of this gamma of y of I of fm minus 1 of x of I plus this function gamma here. And when I have defined this function gamma, then I'm going to update my model. So this is a little bit different from the steepest descent, which we defined before the break. So we update the model f of m of x, which is given by f of m minus 1 plus, and now we're going to plug in a parameter eta, which is going to play the same role as the learning rate. So this gamma of m here is the one which comes from the optimization here. And this parameter which we have here is simply our learning rate. So we update the model incrementally by taking small steps. So this learning rate eta is typically something which we would put between 10 to the minus 3 to roughly 10 to the minus 1. And that becomes a parameter in these gradient boosting methods. And you would typically tune that one in order to get the best possible, let's say, mean squared error or accuracy. But the whole idea now is that if you have these gradients, then you can update the functions with the gradients multiplied with a learning rate. So this is the different philosophy. So it's us using what we have seen before, but using the gradients to improve the quality of the function so that these gradients gradually, as we increase the number of iterations, this residual error is going to be driven to zero slowly. So at the end, what we want to is clearly to have this quantity, which you see here, this one, to go to zero. That's what we want at the end. And that's the basic philosophy behind a gradient descent method. And in a way, this concludes the standard part of the lectures. If you go into the textbook by Rashka, there is an example where they do this gradient boosting with the cross entropy, which you discussed in project number 2. And there is a detailed calculation of the different steps which you get when you include the cross entropy as the function L. So this is something which also renders these methods so popular, is that if you take, for instance, a function like this cross entropy, which we discussed in connection with project 2 and logistic regression, then you will have analytical expressions for all the derivatives. And that makes it much easier to calculate as well. So you would use the sigmoid function as your probability, plug that one into the logistic regression, and then keep iterating. And if you go into Rashka's textbook in chapter 7, you will see the detailed calculation of the steps which we put up here. This step, the calculation of the derivative here, that means this quantity here, and how you would gradually update it with analytical expressions. So if you want to program yourself a gradient boosting, I would simply take that example in chapter 7 of Rashka's textbook, go through the derivation of the derivatives and the analytical expression which you have, and then simply implement it by calling a simple decision tree. Any questions so far? I wanted to show you some quick examples on how you run it, in particular with extreme gradient boosting, because I told you that this is a library which is extremely fine-tuned to this type of problems. And you will see that for the cancer data, you get basically a correct prediction of 100%. And this is something which we want to, obviously. So let's go back to the Jupyter notebook. And simply look at some examples. You will also find an example on how to implement the adaptive boosting here. there is an adaptive example here where we use the classifier from scikit-learn, but there is also an example of how you can write your own program. Actually, the thing which is a little bit depressing, but also good, is that if you question ChatGPT, write a program which implements adaptive boosting. It's going to do a fantastic job for you. And this is actually pretty useful because when you write your code yourself, you can always compare that with an example. And this would be like an example you would find in a textbook. Actually, many of these examples are in textbooks. But it's a very easy way of doing it. With scikit-learn, you have an AdaBoost classifier. And this AdaBoost classifier is pretty simple to use here. And you will also see now that when we use that and plot the metrics, you will see that AdaBoost is actually doing better than a random forest. Then, if we then move down to, this is actually a code for doing it yourself on some simple data. Actually, what I did here was to, I had my own code first, but then I actually asked ChatGPT. And this function is actually generated with ChatGPT, and it does a pretty good job. And you will see the basic steps, which simply follow the algorithm which we set up before the break. So you see the alphas, these parameters which we needed to define, and then it calculates the new weights, it normalizes the weights, which is done here. You can see that one. And then it simply finds the different parameters, and it uses a shallow decision tree as a way to perform the training or the basic trainer here. What you will find here is then just the basics of gradient boosting. And there is a simple, I'm going to skip the regression case, but I'm going to look at the gradient boosting case, which you have if you use the boosting classifier, which is included in scikit-learn. So scikit-learn has actually a gradient boosting classifier here. And in that particular case, you see now that in this case, it actually gives a prediction 97%. But then if you look at the extreme gradient boosting, this is actually a library. So it's an optimized distributed gradient boosting library designed to be highly efficient. So you would actually download it and install it. And the way you would simply use it now is simply like I do here, import XGBoost as XGB. So I have installed the library. And I guess now with Anaconda, if you use that one, I think, I'm not sure actually, but I think XGB follows automatically. Alternatively, you would just do a installation yourself of XGB. And this is just the way you would use the XGB classifier. And again, I'm staying with this cancer data because you've gotten pretty familiar with that and you know exactly what you should expect. And you can see in this case here, you get a perfect classification of 1 actually. So it does really an excellent job. And this is one of these methods which has been winning many, many competitions. If you go to this website, kagle.com, you will see many examples of people having used extreme gradient boosting. So for project number 3, if you want to, you could compare your results with extreme gradient boosting. You could take random forests, the methods you wish to test. And as I said, this gradient boosting is one of these methods which is extremely popular. And its basic philosophy is actually simple. It's something which we could, if we want to set aside just some few days, we could actually write the program for it. This concludes more or less the topics which we wanted to cover. So we've had an emphasis on deep learning methods, but also on traditional methods and also methods which are based on the traditional ones like gradient boosting and extreme gradient boosting, which are very popular for essentially many labeled data problems. However, those of you who are doing the differential equation part in project 3, that's an example where you use a neural network to generate a new solution. So for you solving a differential type of problem, you're actually using a neural network as a generative method, although it's very much used as a discriminative method. So you discriminate, you train a deep learning method to discriminate between this and these cases, but you can also use it as a generative method. And if you solve a diffusion equation, the solution to your diffusion equation is actually a probability distribution. So that means that you are generating a probability distribution with a neural network, which normally is used for discriminative type of problems. That means you have labeled data and you want to recognize whether this was a painting by Van Gogh or somebody else. Or you want to see whether it's a cat or not. So let me just scroll down here a little bit. Okay, so a quick summary. And I actually love this figure here because that reminds me of me when I was a student. And 1 week before the exam, I looked like this. 2 days before, I was like this. And then after the exam, I didn't remember anything of what I did. So the hope with having a project-based way of teaching is that you take ownership in the projects, and then we get rid of this kind of stressful situations. Although probably before 1 week before we have to hand in the project, we as humans, we are probably in this situation here as well. Okay, so the topics we have looked at, let me just increase the fonts a little bit. So we have looked at some statistical analysis with resampling methods, and also a little bit on how we can link a statistical analysis with what we get. Although this has not been the main focus, but we have, obviously, we cannot avoid optimization. And then we've looked at machine learning methods, and we've gone through some basic concepts here. We've looked at, for statistics, we've gone through gradient methods for data optimization. We have used the estimation of errors with cross-validation and bootstrapping. We've been looking at the singular value decomposition and how we can use that one to analyze results in regression types of problems. But we have not discussed principal component analysis. This is normally called PCA, and you will find material about that in the lecture notes, but we haven't had the time to discuss it. We have an advanced course in the spring where we actually use that in connection with a method which is called autoencoders for deep learning. So for those of you who take some of the advanced courses, you will encounter this. So principal component analysis is actually very easy in philosophy. What you do is you set up your correlation matrix like you would do with the cancer data, and you diagonalize that matrix. And then you will pick the largest eigenvalues because that corresponds to the largest variance. And these are the most important features. So if you find that you can go from 30 features down to 10, you have reduced the dimensionality of the problem to 10 most important features. And this is a technique which is widely used to reduce the dimensionality of the data. Now, if you want to use that in the third project, since we have it in the lecture notes, but we haven't covered it, feel free to do that if you're familiar with it. But it's not something we require. When it comes to machine learning methods, these are the methods which we have looked at. We have looked at neural networks, feed-forward neural networks, convolutional ones, recurrent, decision trees, and we have looked at these ensemble methods like bagging and voting, random forest, and boosting and gradient boosting. And this year we have not looked at the support vector machines, and we have not looked at the kernel methods, but we have actually looked at the regression methods. So if you now look at, this is something if you want to, if you look at the kind of learning outcomes, this is our ideal. And then when you read this, you can ask yourself whether we have achieved it or not. So the last weekly exercise is actually you giving a feedback to us. Then take a look at these ideals which we have here and see if that matches with the kind of learning outcomes you feel we have given you. So the way we learn is very individual, and there is not a one recipe which fits all. So, but take a look at some of the things we want you to have gotten a better understanding of. And see if that matches your feeling of the outcomes of the course here. Machine learning is actually, what you see in these slides here is actually something I have to revise every year because it's such a rapidly developing field. And the main goal of this course is actually to give you some of the basic understanding. And then the university has many more advanced courses which can go more into details. Let's say you are interested in machine learning for imaging. So we do actually have 2 courses at the Department of Computer Science, which focus only on machine learning for image classifications. And there are many, many more courses, and there's a list here of different types of courses which you can follow if you want to. If you look at machine learning research, a very popular place to go is actually on ArcSieve, which is a preprint server. There you have hundreds of new papers every day actually on machine learning applications and methods and so on. But typically when you start your machine learning project, and you've probably seen that now working with project 3, you identify the problem, whether this is a classification or regression, consider your data carefully. And you probably noticed that, I saw that at the lab, some of you had data sets which were missing. And what you often do then is that you would take the average over all the other values and replace the missing data with the average. So this is a common procedure in case you have lots of data sets where you see no numbers, or sometimes it even says none or not a number. And sometimes the data are just wrong. So typically if you have a true-false case, you would write in your file 0, 1. And since in many, many cases a human was punched in these numbers, sometimes this human has punched in 2 or 3. And that's definitely wrong if you just want 0 and 1s as inputs. So always look at the data set. We actually had, and this is a very, very sad case. We had a case of scientific fraud in this country in medicine, which was really bad. And this was somebody who has faked totally data about the cancer in the mouth. They'd gotten lots of research funds for researching on cancer in the mouth, but all the data from the PhD till some of the important papers had been falsified. There was not a image in the PhD of this person which was not falsified, not faked. But actually, you could go into the data set which had been used, and you would see that the names were more or less the same for all the patients. So if you had looked carefully into the data set, then one would have seen immediately that the data had been falsified. So consider your data carefully. If you can, look into the data file. As I mentioned in the beginning of the semester, we had the student who wasted 2 months because the wind speed was in kilometers per hour 1 year and meters per second next year. And this person couldn't make head or tail of the regression type of problem which that person was solving. Then you need to choose a model that fits these data sets which you have and the type of problem. So this is in a way you who decides this, and that's what you're doing in project 3, essentially. And then you consider your data carefully again and think of the data representation as well. And based on your results, you will have a feedback to the earliest possible point. So in a way, what you're doing in project 3 is essentially the way you would do research with a data set, essentially. And for many of you, that situation in project 3 is going to be pretty similar to what you may encounter in your master thesis. And this kind of loop is essentially the kind of loop which you would go back and forth within here. So you need to find whether it's supervised. You obviously start with the simplest model. So you start with a straight line if you have a regression type of problem and see what happens. And then you also start with a minimal processing of data, as you did in project 1 and project 2. So all these basic steps which you see here are essentially what you did in the different projects here. You need to prepare your data. You should discuss why you need to center your data, normalize the variance. You can decorrelate data. When do you do train, test, split, etc. So these are all things which we've gone through during the semester, which are some of the essential elements when you are solving a problem like in Project 3. And then clearly the activation functions, if you're dealing with deep learning, which one should we choose? Should we set all weights to 0? That's a terrible idea. You would normally set them to small random values. Which optimization method should I use? A stochastic gradient or just the plain gradient descent? Sometimes gradient descent works well. Then we have hyperparameters, which we're going to tune. We can have soft classifiers. We can have the depths of the trees and many other parameters. So soft classifier against a hard classifier is something which we discussed last week in connection with this voting problem. So a hard classifier is just to pick the one which has the most votes. A soft classifier would be like things you would have in Norway in a multi-party system, where you have a representative democracy. A hard classifier is what you would have in the US and in the UK, where the winner takes all. And then you can have, like the Labour Party in England had 33% of the votes, but they got 65% of the members of parliament. So that would be an example of a hard classifier. I hope I was not too political here. I try to avoid that. But then we have important methods. So cross-validation is one of the most used resampling methods. I also wanted to point to courses which you can, if you like this topic, there are many options for additional courses. So if you're looking at imaging, we have this course which is called IN4310, which is called Machine Learning for Image Analysis, and that runs in the spring. So this course here forms a kind of background for taking that course, because they would typically spend just a week or 2 weeks on neural networks. So if you haven't done them before, it can be a rough start. And then it moves quickly into CNNs and RNNs and other methods. But that's a course which many of you end up taking if you are going to deal with image classifications, which is a very, as we said, one of the big contributions from machine learning to, humanity is the capability to discern between different types of images in connection with medical research. So the way to discern whether this is a benign or malignant tumor has been a huge benefit to medical research. So in medical research is one of the cases where we really see a huge benefit of many of these methods, a kind of immediate benefit. Because as we mentioned in the beginning of the semester, many hospitals, actually worldwide, struggle in recruiting pathologists, which are the experts which can see from the tumor or from a given image whether this is a benign or malignant. And that takes a year-long training to train somebody as a pathologist. So if you can use machine learning to screen the bad and the good cases, then you know exactly what kind of treatment that patient needs. And then you can avoid long suffering and anxieties, obviously. We have a very interesting course on deep learning for autonomous systems, which runs at the, we have an Institute for Technology, which is actually close to the city of Lillestrøm. We have an advanced course for deep learning, which unfortunately runs in the fall. So this IN4310 runs in the spring, and then the advanced one runs in the fall. But these are two actually very popular courses. And we have also, if you're interested more in applications to physical sciences, we have this Physics 5429, which runs in the spring. So that builds upon this course, and it's a very project-based course, and it focuses more on generative methods. But it has also focus on deep learning methods, but then it moves quickly over to generative methods. Then we also have courses on statistics. So there's something which we have not covered much, and that is a Bayesian analysis. And this is a topic which is, how to say, Bayes' theorem is, as we mentioned earlier, is like Pythagoras in geometry. Bayes is the same as Pythagoras in geometry as Bayes is in statistics. And it's used to allow you to extract a probability distribution with some basic assumptions about the prior probabilities. But this is a very popular course, and unfortunately that one, SDK 421, runs in the fall, but the one on computational statistics runs in the spring semester. So if you're interested in these topics, and the one on computational statistics has many of the elements which we have not covered, like Monte Carlo samplings, etc. So there's a lot of things to choose among if you want to continue with machine learning in either research or you're just basically interested in that. So this is a very dangerous thing to say something about what the future is like. This is something which has been developing over the last decades. So convolutional neural networks have been extremely popular, both in image and video data processing, and have also been applied to sequential data, such as text processing. These courses which you have here, IN 4310, covers convolutional neural networks, and the same applies to this course here, Physics 5429, because image recognition plays an important role in many, many different fields, either from scans of the brain to you classifying a specific event from a particle detector. So people who do analysis of experiments in CERN, they often have images from actually the energy deposited in the detectors, as are represented as images, and then you can use these images to classify what kind of event took place. And then recurrent neural networks, which came in the end of the 90s, they actually used to process sequential data, and they have actually been used in language understanding, and it's also the stepping stone towards large language models. So recurrent neural networks are also things which are discussed in these advanced courses. If you look at both the Physics 5429 and this IN 4310 and IN 5310, and also this TEC 5040, they cover recurrent neural networks. And then we also have something which is called the encoder-decoder framework, where essentially the building block is a neural network. And you saw that with convolutional neural network, that at the end, when you flattened out everything, you reduce the dimensionality, you are training the model through a standard neural network. A recurrent neural network is also, in a sense, a network which has at each time step, if you think of that, a neural network. And same with an encoder-decoder. And these are also widely used. And we have several courses which cover these methods. So these three categories of methods here are widely popular. And there's a lot of research going on. Whether the field is saturated or not is something which we cannot tell. But there is a consistent and widespread research. So the typical problems we often deal with are classification, regression. We have not covered clustering. But the topic which deals with unsupervised learning is often the one which is a little bit more interesting for many of us, because we don't have the possibility to label the data. Also, to deal with generative models is something which is very, very important. So if you think of a software like DALL-E, which many of you probably have used to make new images, then you would just write in the prompt, draw a cat with 5 legs for it, and it would do that. But what you've done then is to train a probability distribution, which then allows you to generate new cats. So the name generative means that you have something which allows you to generate new solutions to a problem, or new images of cats, for instance. And these unsupervised learning algorithms, they're often more related to so-called generative methods, and Boltzmann machine is one of those. I'm not going to go through everything. You can actually read through it. This is actually the topic of this course, Physics 5429. There we go more into detail into generative methods. I'm going to skip some of these things here because there's a lot of, information. But take a look at this overview over different methods. And these different methods are then covered by different courses like reinforcement learning. Many of you will hear about transformers, transfer learning, adversarial learning. And there's obviously quantum machine learning, which is also a very hot topic, and et cetera, et cetera. So I would like to say that the last word is actually the best way to predict the future is to create it. So in a sense, since you now taken one of the first courses, this course is actually a kind of basic course, which gives you a feeling of what is going on. Then the nice thing with many of these machine learning algorithms and also the more advanced ones is that there is so much things going on that you, at the stage where you are now, can actually be part of the community which develops new methods. So I think there is a lot of topics to address. There's a lot of interesting applications to scientific problems. I use machine learning to solve quantum mechanical problems. This is something which I would not have done 5 years ago, just to give an example. And the type of applications are so many that sometimes it's a kind of, you ask yourself, where should I start? Because it looks overwhelming. But just start with your thesis project, and then gradually from that one, you will often see new connections and new possibilities. That's my basic advice. And the thing now is that there's so much going on, and the field is also not yet settled. Like if you look at classical mechanics or many of the mathematical methods, they've been around for hundreds of years. And you have a wealth of well-established theorems, et cetera, which sometimes can be intimidating. This field is still a field where there's a lot of explorations which can be done without us not properly understanding why it works or not. And if you look at some of these methods like gradient boosting, it's very intuitive to actually do that. And, or even this ADA boost, many of these methods actually, when you look back at them, they're not that complicated, but still they work. And one thing which we have not discussed very much is actually the ethical aspects of many of these algorithms, because we've chosen to focus more on the mathematics and the programming of them. But clearly, when you do convolutional neural networks, for instance, there are lots of ethical aspects. How do you use face recognition algorithms? You can use them in mean ways, or you can use them in positive ways. Many of the algorithms which we have developed for, let's say, medical research can also be used for face recognition in ways which we perhaps would not agree upon. So there are lots of ethical aspects which we have not covered. And that's a little bit deliberate because this course focuses more on the basic mathematics and letting you understanding what are the pros and the cons of the methods. Because our feeling is that if you understand the pros and the cons, you know where the limits are, you know what needs to be improved, and what we need to be a little bit more careful with. So I hope you don't get disappointed, or you're not too disappointed if we didn't discuss many of these ethical aspects. It's not because we don't want to, but this leads quickly to just a course by itself. And to me, it's always a little bit sad, as I wrote in the email, when the semester is over, because it's been such a pleasure to meet you guys. And I will probably see many of you the next semester as well. So thanks for all the heroic efforts, and best wishes and good holidays to everybody. By the way, the lab runs this week, but also next week. Okay, guys, take care. Thanks.